Hi there, welcome back to the breadboard. In a previous video we looked at the Kunbus Revolution Pi and the Kunbus RevPi Connect, both modules using the Raspberry Pi compute model revision 3. In this video we're going to start looking at how to program the RevPi and the RevPi Connect using Node-RED and utilizing the built-in kernel runtime that has been added to Raspbian by Kunbus to allow communications and aggregation of all of the data from the various I modules that you may have plugged into the controller. We've already shown you how to back up and update the firmware and update Node-RED to the latest version, and if you try and follow on along with me, I will assume that you have done that as well. And it is important that you do make a backup because, hey, if we get something wrong, it's going to be easier to restore from the backup necessarily than trying to command line undo things in Linux. Next, what we're going to do is we're going to look at the environment that we're going to be using. I've actually wired up the panel. I can show you that right now, what I've done. So here is a full view of the panel. I'm just going to zoom in on this area down here in just a moment. What we have is our mains coming in, just a little utility socket up here. We have a 24 volt 10 amp power supply for driving I/O devices. Don't have much connected to that right now as far as a load is concerned. Okay, so what we have is the Revolution Pi Connect has got an AIO module and a DIO module connected to it, same as we had set up in the previous videos, and two of the analog outputs are being sent up to the Lascar dual display module, and that takes in two analog inputs. It's programmable, and I've set it up so that it will display effectively air temperature and air humidity from a sensor that I have outside the house measuring the temperature and humidity. It's connected via MQTT and is based on an ESP8266 Sonoff module. I've just added a DHT22 sensor to it. The next thing that's connected is I have internally right here an infrared temperature sensor from RS Components that is measuring just the ambient temperature here. It's actually just pointing at this piece of wood behind it in this view, and it's contactless, so it's showing you that effectively the surface is 21.3 degrees centigrade. It is configured to give a 0 to 10 volt output based on a temperature reading of 0 to 100 degrees centigrade. And the next item is a rotary encoder, which is connected to two of the digital lines right here. And this module will be configured to actually support the rotary controller so that when you turn that dial, it will either increment or decrement a counter, which you can have access to through your programming to see how much the knob's been effectively turned. One of the other inputs on this analog module, you can't see it so well here, is a resistance temperature probe, which is actually sitting below this module, which is measuring the temperature of the room as well. Now I do have another diagram for that, so let me just bring up a block diagram of all this so that you can see easier how I got everything connected. Okay, here we go. This is basically the sort of a diagrammatic view of what we were just looking at with the physical hardware, where we have the RevPi Connect, which was on the right hand side of the other diagram, connected to the AIO, which in turn is connected to a DIO. We have a PT100 resistance temperature detection feeding into the RTD input 1 of the AIO module. We have the analog 1 and 2 feeding out to the Lascar panel pilot display. We have an analog input feeding into the AIO module as well from our contactless infrared temperature sensor, and we have the rotary encoder feeding into the DIO module. On the RevPi Core 3, we have the DIO module feeding D1 and D2 out to the control inputs of two mains relays, and that feeds then in turn a socket. Both subsystems are powered separately from their own power supplies, as I've already shown you, and all of the I/O is powered via a third power supply giving us 24 volts at 10 amps for driving that. Now, the reason I've done that is because these are just small power supplies driving the logic of these two modules on their own. And I also want to be able to keep isolation between the I/O outputs, the physical I/O, and the control logic, so that if I did make a mistake up here, I'm not going to take out one of the controllers or anything like that. It also keeps noise crosstalk to a minimum and all that kind of stuff as well, especially if you're switching some higher current loads and things like that on this side of the power. So that's what we basically have set up here. We've got Node-RED running on the Connect and also Node-RED running on the Core 3. So that pretty much covers everything that we have wired up. I also have remotely connected a Sonoff temperature sensor using one of the Sonoff THT16 modules, which is running a temperature and humidity sensor. It's sending its data over the Wi-Fi network over to an MQTT sensor that is running on a separate Raspberry Pi. I haven't loaded it into here because I wanted to show you how you can actually remotely access things like MQTT and other services as part of what this video is all about. What we're going to have is the RevPi Connect reading some sensor values, both from the remote temperature sensor that's outside and from the local temperature sensors, both the RTD and the contactless infrared sensor, and feeding that information not just to a local display here, but also to a web page on the RevPi Connect running under Node-RED. And some of this information is going to get forwarded to the RevPi Core 3 to display on another web page that's running on here under Node-RED. But also I have configured a pair of switches under the web page of this Node-RED instance that, when pressed or clicked on and off, will actually control these two relays on this remote server. So it's going to use Modbus to send the signals across to this Ethernet IP module that will then, on a polled basis, be interrogated by the RevPi Core 3 and brought up into the Node-RED environment. So enough of how we've got this thing configured and wired up. Let's get into the actual programming. So the first thing we're going to do is go look at the RevPi Connect configuration, look at Node-RED, look at how I've configured the hardware using Pictory, and I'll just run through how that's all working. Okay, so this is the display that I have created using Node-RED. As you can see here, I have a few extra things on here as well. We'll just ignore this for this video. We have the encoder value, which is numeric, and we've got it displayed here. Currently, I haven't twiddled the knob or anything. We have two switches, which will, when pressed, send a signal via Modbus to the other Revolution Pi, the Core 3, that will then be interpreted to turn on and off the digital output 1 and 2, which controls the two external relays. We have the IR temperature sensor being displayed here as a trend, and we have the RTD temperature also being displayed as a trend. Now, obviously, they're sitting right next to each other, so they're pretty much reading the same value. Now, the one thing that you can see here is that, even though they're within an inch or two of each other, the RTD is showing much less deviation in the value. Now, part of that is because the RTD is not showing the same resolution of readings compared to the analog input. This one is actually being literally interpreted as a resistance temperature detection device by the AIO module. Also, the IR temperature sensor will react far quicker to a temperature change. Even a breeze just blowing in front of the sensor would probably impact a little bit of the noise on here, whereas the RTD probe, because it is based on a resistor which has a certain amount of mass that needs to be heated up or cooled down, will react a lot slower relatively to the IR sensor, and therefore it's going to give you a smoother graph. The two half donut dials here are showing the outside temperatures. It's actually in my garage, but it is outside in an unconditioned space. So it's currently at -3 degrees centigrade with the humidity at about 49%. So the code, let me just make this full screen because it's going to be looking a little easier to look at this code. We have a number of things in here. Now, some of these tabs are going to be covered in other videos. They're just all here because I've been slowly building up some sample programs for us to have a look at. So the main part here that I just want to quickly cover is we have a number of Sonoff devices around my home that are feeding data to a MQTT server running on an external Raspberry Pi. This node here, which has got tele/hash on it, is subscribing to that MQTT server and bringing in any messages that begin with tele/ and then anything after that. I have a select unit which looks at the topic of those messages, and if it matches one that I'm interested in, then it will switch it to the relevant outputs. And then the next parts of these are basically stripping that message down further and feeding them out to temperature, humidity, time, and relay display components. So this is the Node-RED dashboard down here. You can see, where is it here? This is the Node-RED dashboard library that has been installed into Node-RED. I'm not going to go in this video how you put in different nodes and things like that. There are plenty of them around at the moment. So I'm showing the relay status, the sensor readings, and other stuff. I've got a power monitor here as well, which is being showing volts, amps, energy consumption, etc. for some other sensors that I have hooked up. Status is basically the same kind of thing, but it's just right now it's just configured to show relay status in response to commands being sent. And then I have if I press one of the buttons on one of the Sonoff modules, in this case I have a motion sensor hooked up to one of them. If it detects motion, it just feeds through this flow. So what am I doing here with relevant to our Kunbus test? I have in the tele, where we're receiving the temperatures, one of the modules, which is the garage sensor, I have fed a link so the message that comes out with temperature and humidity, I have fed to the Kunbus flows on here. So the signal for the temperature and humidity from the garage come in on this node, and I've got two things. I have a temperature sensor which takes that value directly and displays it up on a graph, a dial, and the humidity. We just looked at those a moment ago up here. So that results in this display here from -30 to +50 for temperature, because it's Canada and it's outside and it's winter, and the humidity between 0 and 100%, so currently sitting at about 49%. These are actually live readings as well, so this is what it is in the garage right this minute. So one of the consistent things we're using here is a exec command to talk to the process that runs on the Kunbus Core 3 or the Connect that talks to the control logic. There's a process running in Linux on the Kunbus version of Raspbian that polls at a fairly fast rate all of the I/O that is configured on the modules, and it brings all of their readings for both inputs, outputs, analog, digital, counters, the RTDs, etc., all into a memory location, and it's represented to the other applications as a file. This is a fairly typical thing for Linux applications, and in order to access that file, I'm using a program called PyTest. So in here you'll see it's PyTest, and then these are some of the parameters that are used. I use this as a little bit of a test program in the previous videos to just check some of the I/O is working and not. And what I'm doing here is I'm just calling it from Node-RED, and then the parameter that's missing at the end here is going to be provided from the flow automatically. So it's going to be appending message.payload to the end of this. And what I've got here is for temperature, I'm scaling it to be 0 to 10,000, representing the temperature range, and I am then prepending it with output value _1 and then plus the value that I calculate. And then I'm sending it out, and I'm also giving it a topic of THD161157, which is the Sonoff module that is providing the data. And then I'm just sending that on. So we end up with this output value _1, comma, and then whatever this value is. So right now, it's going to be representative of -3 degrees. So that comes into the right, and then you end up with a PyTest-1-Q, which is just quiet mode, -W for write, and then it'll say output value 1, comma, and then whatever that calculated value is. For humidity, it's doing the same basic thing, only the message is output value 2. And then it's going to send it out as well. What that does is when it writes to this, the underlying process that's running in the core is going to be detecting that change in the memory location that the Pi test changes, and it's going to actually send it over to the relevant module, and then that module will set, in this case, the analog output to those values. Now, if we go into Pictory for a moment, this is the standard management for the Revolution Pi. It allows us to configure the modules and also allows us to see what the variables are called. We come in here. This is the one for the Core 3, for the Connect module that we're currently using. And if you select the analog I/O module here, you can see you've got input values 1, 2, 3, 4. So we've got the 4 analog inputs. We have the RTD values. This is what we would use to. This is what we're going to be using for the RTD. And you have output value 1 and 2. Now you can. One of the things you can do when you're running Pictory and configuring this is you can actually preset some outputs or inputs to certain values that would be effectively the power on state. So right now this is set, so it will output 5 volts on output value 1 and 2.5 volts on output value 2 at power up. Now you don't have to do this, of course, but I just did that while I was experimenting. The input multipliers are relevant to the inputs. There's a lot of different things you can configure here. The outputs I've set from 0 to 10 volts. As you can see, you can pick a lot of different ranges for this. The same for output 1 and output 2. They're both set to a 0 to 10 volt range. The RTD is set to a PT100 4-wire, and that uses effectively a Kelvin connection. We're going to get into Kelvin connections in a different video. We're outputting a voltage on output 1 and 2 of the analog ADC, DAC module. So the name that we need to use for that is output value _1, output value _2. Now I could change this to say temperature 1 and temperature 2 or anything else I want that will fit in this text box. The only condition would be that it needs to be unique across the modules, but I can make this a different name if I wanted. For now, I'm just leaving it at the default name. For the digital I/O, it's the same story, but obviously you can see here that the naming convention is slightly different. We have counters that you can set up. We've got the inputs themselves, and this is the name of them. We have a number of counters, up to 16 of them, which matches the potential inputs. Now we only have, I think, 14 in and 14 out because it's an I/O module, not just an input or an output module. And then we have the outputs, so they're numbered from 1 through to 16. We then have things like PWM. Then we have the configuration part for these. So in this case, I've said input mode for bit 1 is an encoder, and the same for bit 2, because you need 2 lines for an encoder. Where it says direct, it means it's just a binary input-output. Where you set up an encoder, it means that those inputs are going to be monitored by the local microcontroller on that module, and it's going to be incrementing or decrementing depending on how that dial is changed, which means that you don't read the value from I1, I2, I3 anymore, because those are all Booleans, as you can see here. what you would need to use is, I think, the counter input. Yeah. If you had set the mode on one of those to simply be, if I drop this down, a counter, you can count on the rising edge or the falling edge, then it would just be one bit influencing it, and it would only count up. It would not count down. But because we set it to be an encoder, it will go up and down. The outputs I've also got set as direct. I think the outputs just automatically become PWM if you set one of the, if you write to the PWM. So I'll have to experiment with that in a separate video. I haven't really played beyond the outputs being a direct output at the moment. Anyway, so what we're interested in right now is the fact that we've set that up for an encoder for the digital I/O module in this case. And the Revolution Pi itself has its own variables too that you can check out and read or write to. We're not doing anything in this video on that. So the real thing that we're interested in is the fact that these are the variables that we're using for the two analog outputs that are feeding to the last guard dual channel display. So that's what this does. So this, as we showed you, is output value _1 and output value _2 for the humidity. Then it's being put to here. That goes out to the core that's running in kernel mode, and then that effectively gets sent out to the last guard display, and it will end up showing the same values as this if everything's working properly. The RTD and the zero-touch infrared sensor are both inputs. So where do we get those from? And what I've configured here is a read. The command format is pretty much the same. It's still PyTest, but it's a -R for reading instead of a -W for writing. And the encoder, which I'm polling every once a second, is, it's using counter 1. Remember I said that I'm pretty sure it used that? Well, it does. And it's bringing up a 16-bit word. The temperature is being read every second. This is the infrared sensor. So it's just simply reading input value 1, which is set up as a 0 to 10 volt analog input. Nothing special particularly there. And then the RTD, which is on RTD value 1 in this case, which is a completely separate analog to digital converter configured to drive an RTD sensor, and we're polling this at a 10-second interval. There's no point in polling the temperature sensors any quicker than that. Really, things don't change too much, but you can configure it to whatever you want. So we read the value, we get a response coming in from there, and then we process a little bit of scripting on here. So we get the value. So we're getting an integer out of the return value. If it's not a number, in other words, something didn't go right, then I put a 0. Otherwise, I get convert the payload into an integer, because it's got a carriage return after it and things like that. So we're just doing a cleanup and converting it to an int. Then we're just putting it back in the payload and returning it. So that's really all it's doing, is converting the answer into an integer. We put it up to a message payload debug box so that we can actually look at what's being read if we want to. We're also sending it to the Ethernet IP test Modbus, which we'll have a look at in a moment, which sends out our values across the network using Modbus to the RevPi Core 3. The answer to this we put into another switch node, and we look at the topic, which we set back here. The topic just gets passed through when you use this. We've got 3 topics that could potentially come through: the encoder, the temperature, and the RTD. And it puts them onto separate outputs. The encoder goes straight out to a numeric display. The temperature goes through another exec block, which divides it by 100, which gives us our fractions as well, because it's giving us effectively millivolts, not volts. And the other module is scaling it and adjusting as well for display properly. One other thing that I've done is that I found an issue with was occasionally the RTD would give a little bit of a false reading and mess up my scales. It would suddenly think for one sample that it had, say, 500 degrees centigrade. It might be a little bit of noise in the environment or something. I'm not sure what's causing it yet. So I just put a little bit of a test in here that if the message is greater than 100 degrees centigrade, then just null out the payload. That goes into the two charts and also potentially a debug message. So these charts are these two. So that's what they're feeding. And as you can see, it's working quite nicely. If you wanted to see what the values were that were coming in, let me just clear that out. This one on, it'll show what's coming out of here. There you go. So you can see the reading. That's 2091 and 21,000 and 2,120. That's actually 20 degrees 0.91 and 20 degrees 21 degrees 0.2. So if I turn that one off and turn this one on, we'll see what comes out after this scripting is done. You can see here now we've divided by 100, so now we have the fractional components of the reading as well, which we can put up to the display. So great, that's all working nicely. This has all so far been working just locally, displaying on the web instance of Node-RED and really nothing more. We do have a link out here which we'll follow in a moment. The other link which we showed earlier comes in here. We've already discussed this, which writes out the analog values, which gets displayed on the LASCAR panel meter. These two bits down here are just testing, where I was playing around initially to figure out how things work well. So we'll ignore that for the moment. So we've got our local display covered. Now, how do I get information from this RevPi Connect module across to the RevPi Core 3? And as I said, we're using the Ethernet module. So let me just bring up that display so that I can show you. The first thing is the pictory for that. So here's our three modules. We've got the RevPi Core 3, the DIO, and the Ethernet IP. In the Ethernet IP, it's a little weird how this works, and I'm not going to try and explain it all right now because it kind of gets my head all, gives me a headache.
All of wibbly wobbly, timey-wimey stuff
when I try to think about it. But same thing applies here. We've got named variables which show up in the core file process that we can address using PyTest, for instance, in my case. And you've got inputs and we've got outputs. Now currently this is configured for only having 20 inputs and 20 outputs. You can add more if you want, up to, well, you can flip it to use 480 if you want to, if you need it. These inputs and outputs, if you look at them, they're all bytes, and that is because primarily this module is an Ethernet IP. Now there's a lot more to it than just bytes, of course. When you're using a client application, and as I said, we're going to do this module in a separate video, you configure a whole bunch of objects and classes and a whole bunch of things like that. For this video, we're just looking at the Modbus part of it. So effectively what happens when we talk in Modbus is Modbus supports registers or coils, which are basically words, which are 16-bit, or booleans, which are 1-bit. And the way that this works is that it actually overlays the coils and the registers on top of each other. So if you're using it in binary mode, so we've got one input here, say, that is a byte. These two together, Modbus together, would have input 1 and input 2 combined. That would also be 16 bits. You would just use a different offset in the command to set the bits, which means you can bit manipulate the word. Okay. As I said, I'm going to get into that in a whole nother video. I don't want to dominate this with going through how this all works. Same thing for reading. What happens is the concept of inputs and outputs on this are that when the Core 3 writes to this, it effectively sets it to its outputs because it's coming out from one side. It's the master on this. The right side, if you like, is going to here and it's writing outputs, and it can read the inputs. When something outside here is writing to this, it effectively would ask for inputs and write to outputs. So it's kind of crossing, it's a crossover. Think of a gateway or something like that, and they're swapping around when the values come in and out. So it got a little bit confusing. Now, the other thing is that this module also has its own web interface that you can look at directly. So this is me talking directly to the web interface that's on that Ethernet IP module, and it actually shows me locally the Modbus values. So if I go to the main page here, log back in again, session expired, these are all Modbus registers, and you've got the range for each set. So we've only got 20 IOs. We go into the first one, which is the one that I'm using. All right, you can see I've mentioned, but I haven't shown you how it's working yet. But these two values here, output 1 and output 2, are the two registers that are being written to from our RevPi Connect. These other values here are just internal preset ones that I had set in Pictory for it. So if I go into here and I look at Pictory, you can see I've got on the outputs here, I've set 65,535, which is the 2 bytes of 255. Remember that I said under Modbus they get each pair of bytes get combined together. So because they're combined, the effective offset sequencing will be slightly different, because this is showing you the Ethernet IP values. So I've just pre-configured a few different values here as writing on these outputs. But when I look in the Kunbus configuration, you actually see these showing up on the inputs. Now remember what I said about them being crossed over as they pass through the module, and this is what I'm meaning. It's actually crossing over. And if we go back in here, you'll see that the inputs, the ones down here, I put some preset values, but they really don't have any effect. And it's input 1 and 2, 3 and 4 that I'm writing to with the digital values. Now I'm also using a few of the bits on the inputs to pass across the digital data for the I/O that's going to be ultimately sent to this module to control the relays. And you can see here right now it's showing a 0, and we'll get into that in a moment. And so going back to here, we can see that we were getting, let's just pick up the latest value. Okay, it's just written a couple of new values. So it's written a 2100 for the temperature and a 2120 for the RTD. And if we go across to here, we see, oh, it's just sent another one, 2120 and a 2108. And there's just updated to 2094. So you can see we're actually getting the data coming across to here from our RevPi Connect. So how's that happening? Well, remember we had this link going out here for the two values that were being written. And if we follow that through, we come in here and we got a switch. So we're just selecting, are we doing temperature or the RTD? And we have two Modbus writes now. This is going to use TCP/IP, Modbus over TCP/IP. So we've got write a single register. Because we're writing, they're offset high up. So this is address 1024. And if we look at the Kunbus here, our write registers are hex 4001 and 4002. So that translates to the decimal 1024. And if we look at the other one, this would be 1025. Okay, the server I've configured is simply the IP address of the Ethernet module, Ethernet IP module with its port, and just giving it some information, told it I'm using TCP/IP, and that's pretty much it. So then we've just, when it writes, and we just got to debug if we need it. The two power switches here, when I click them, they're going to send a true or false. The topic is going to be the write register for the bit. Now this is way up because it's using bits, and so the module, the Ethernet IP on its Modbus, when you're writing bits, they have a separate set of registers that effectively map to the word registers, but it does a little trickery and sets the bits and everything. So right now they're both off on these switches. And so as we saw here, so this is writing to 16416 and 1641, where is it? 7, I think. Yeah, 16417. And these are going to go through here, which sets up the values for the Modbus. So we're setting the type of write, which is a 5. The address is coming from the topic, and we're just writing one value. And I'm converting true or false into a 1 and a 0, which is what it wants at the other end. So when that goes through is when I click these buttons, and those are controlled from here. So here's the 2 buttons right here. Now, where was it we were looking? Here. Right, so now we're looking at, this is the register that it's writing to, but it's way higher than that, but it gets mapped down to this one here. So when I click on power 1, I'm going to be setting that output. So it's going to be picked up by Node-RED. It's going to go through and end up here, which is then going to be sent via Modbus to the other module. So let me click that, and we should see this bit being set. This is the Ethernet IP module, not the physical output yet. This is just the register. So when I click this, there we go, see it's set to 1. And if I unclick it and set this one, you'll see it sets a 2. And if I do them both, it sets a 3. So that shows you that it's actually mapping the binary values into that register. All right, so if I leave them both on for the moment. Now, what happens at the other end for that to work, we'll go into in just a moment. I just want to make sure I've nothing else that I haven't covered in this yet. Oop, come on, there we go. So that's everything that's happening here. These are just tests. So let's go look at what I've done on the RevPi Core 3. Okay, so here we are on the RevPi Core 3 instance of Node-RED, and I only have one flow set up here, and it's a lot simpler than the one we were just looking at that was on the RevPi Connect. So we have 2 basic flows, this one at the top here, and you can see it's polling about once a second, and we have a second one at the bottom here, which is also polling on an interval as well. So let's just work through the top one. This one is dealing with 2 things called power 1 and power 2. So this topic is power 1. It's polling every second, and the payload is 4,0. Now, what we're doing here is we're actually interrogating the Ethernet IP device. So if we bring up the Ethernet IP interface again for a second, here is the bits that we're looking for. And because the payload that we're sending is 4,0. Now, we're actually doing a slightly different kind of read here. We're actually doing a -G for get, which is going to get a bit, not a word. And the way that the parameters work is that you're still looking at words, but you also then specify the bit after it. So going into here, you've got word 0, 1, 2, 3, 4. So the low half of this one is a 4, because the command for reading bits in RevPi in PyTest is a word at a time. Is a byte at a time, not a word at a time. So it's byte 0, 1, 2, 3, 4, and we've said 4, 0. So bit 0 of byte 4, and this one is reading bit 1 of byte 4, and it's going to read those every second and pass it through this flow. So what we end up with is in here, we come through, this is going to do the read, and then the output is going to get fed to this function block, to a template, and also to a debug window. So if I turn this debug on, you will see that we've got a 1 from each of them. If I go back to here and I turn one of them off, let's turn off the bit 2 and go back into here. Sorry, showing you the display there. Here now you've got a 1 and a 0 coming out, and if I turn off the other bit, you'll see that there's a 0, 0 now coming out. So you can see that we're passing this data across using Modbus into a memory location via the Ethernet IP, and here we are picking up that memory location and bringing it through to the Node-RED flows. So what are we doing with this before we do anything else with it? First thing is we're putting it into this template. Let me just turn off the debug there. This template is very, very simple, albeit long, but it's simple. We have a table, HTML, which has got relay 1, relay 2, and a class and an ID. And the code, here's the classes. We've got LED off, LED on, and an LED undefined. And a little bit of scripting that every time a message comes in, it will have a look at the message. If the let's have a look here. If the message exists, it's going to trim it, and if it's a 1, then it wants an on, otherwise it wants an off. It looks for the class based on whether the data is on or off, so it's concatenating LED dash plus whether it's an on or off. And then it's modifying the element by searching for the element name, which is based on the topic, and then the class. So we pop down here, and then you can see here we've got the ID, power 1 and power 2, and it will turn the LED on and off. Now this is a dashboard template. I've lost it here. A dashboard template, so it will show up on the dashboard as part of the web UI. And for this particular instance, we go here, and this is what it ends up doing. So you can see they're blue right now, they're both turned off. If I go over here and turn one on, completely different instance. There we go, we've got it on. If I turn the other one on, we can go back over here and we see they're both on. So that's what that does up to that point. Now the next part of this here is we go through a function which sets up some parameters here. My state is set to the payload, my device is set to the topic, and the payload is my device plus my state. So it's setting up a string to write to a memory location. All right, now if we go back to the very beginning, the topic is set to be power 1 or power 2. Now when we looked at Pictory before, there were no parameters named power 1 or power 2, but I did mention that you could rename them if you wanted to. Now if we go into the Pictory for this node instance here, and we look at the DIO, oops, log that back in. Okay, the DIO, you will see that there's my input. So if I scroll down here, there's my counters and things, and then here's my outputs. I've actually renamed output 1 and 2 to be power 1 and power 2. All right, and in my code here, I'm actually referencing them by name. Remember what I said, this topic will flow through unless something changes it. So it's flowing through the read, coming into the function block, and now it's going to say power 1, comma, and then whatever the value is. This one will say power 2, comma, whatever the bit value is. And here we're doing a bit write with the W of 4, 0 or 4, 1, and outputting that, and that will actually write the physical digital I/O of the DIO module, and that is connected in turn to the relays and will turn them on or it will turn them off. So we have the template showing what it's doing, and we have a way of writing directly to the hardware. So we're picking up from the Ethernet IP over here, and we're dropping it right back down into the DIO module here. Now there isn't a way of programming the Ethernet IP to directly go to the DIO. You have to use a process. Now I'm using Node-RED. This could equally be a Python script, it could be C, it could be any of the numerous programs that are available to run on Raspbian, all right, including some of the ones that conform to IEC 61131-3 programming standards, etc. So I'm using Node-RED because it's free, it's very easy to work with, and it is designed for like the Internet of Things kind of programming. So that's this flow here. Now the second flow, where we have the temperature, this one is purely right now for writing to the web UI over here with these two charting graphs that are going to be on the web display. So again, we've set up to read. So in this case, we're reading from 0, 2. Now it's going to be a different command, so this is not going to mean the same thing as we had up here. and the other one is reading from a 2, 2. Now this is saying, because we're talking to the Ethernet IP, if you remember what I said, that from internally everything is a byte, not words. Even though Modbus wrote to it as a word, here we have to pick it up as 2 bytes, and then we have to join them together afterwards. So that's going to go into this read, which is doing the -R. Now if you've got -R, comma, and then just a 0 or a 2, it'll read a the full byte, but only 1 byte. If you put a comma and then a value after it, it will read 2 bytes. You tell it the quantity, basically. If you put a name here of a variable, then it's just going to read the variable and you can't do anything else with it. Like up here, we've got power 1, power 2. Here we're using an offset. All right, so we're reading the RTD value that's being put across. And if you remember, we saw that in here. So here's the contactless IR sensor value, and here is the, sorry, this one is the RTD, and this one is the contactless infrared sensor. Now why is this one reading much higher now compared to this? I moved it and put it pointing down onto the power supply, which obviously the case of that is running a lot warmer than the ambient. Well, about 8 degrees warmer, that's all, because it's not heavily loaded. So it's reading the values, and we can see what it's reading. Let me just turn off, those are turned off. Let me just clear this. If I turn this on, these are reading every 10 seconds. I can trigger that actually by just clicking these. So you can see here, we've got these 2 values being read. So 62 and 8 and 111 and 11. Now these are both, we have to add these together. We have to multiply the second one, which is the high byte, by 256, and then add it to the low byte. Right? So you got 8 and 62 and 11 and 101. And when you do that, which is in this function, okay, let me just pull that out a little bit. You can see here we've got get the payload, trim, so we're getting off any white space from it, and you're splitting it into 2 characters, because right now it's coming in as a string. As you can see here, it's 101 space 11, and it's got a hard return in there as well. So we're trimming off the white space. We are then getting the values by using parse ints, array 0 and array element 1, and the second one, which is the high order byte, we're also multiplying by 256. We're putting that value back in the payload and letting it flow on. All right, and when it flows on, now remember there's a topic in here as well that's flowed through. We go to this switching block, which allows us to send encoder information, temperature information, and RTD information. Now I don't have an encoder one set up right now. I just copied this block from the other node red. So we've got the 2 temperatures. We come through another block. We divide it by 100 again, because because these are dealing with just ints in the registers, we cannot send over a floating point value. So I multiplied it by 100 before we sent it, and then we just divided it by 100 to be able to display it again. And same for the RTD, we just divide it by 100, and there we're done. And then it goes through to these 2 graphs. So when we look at the dashboard, this is exactly what we're seeing here. This is where I started after saving the flow. It was about just after 4 o'clock this afternoon. It's now just coming up to 9. This is where I moved the infrared sensor. I think I've got those the wrong way around. I moved the infrared sensor onto the top of the power supply. Yep, get that right. And this one did not get moved, so you can see it stayed fairly static, because there's not really any change in temperature right now. What I wanted to show you here was how you can do some fairly straightforward programming and get this to work across 2 different nodes, across multiple nodes and across multiple instances of a RevPi Core, Core 3 and a Connect in our case. They could be, of course, any combination of the different types of Kunbus controllers. The principles are the same. As long as you can run Node Red on it, then you could replicate what I'm doing here. The key, I think, some of the key points that I want to highlight is this reading that I'm doing using the exec function, using the Pi test, is potentially not the most efficient way of doing it, but there aren't any nodes yet for directly using the or accessing the file system. You would need to use IO control from a Linux perspective and a file reader to scan through, and you'd probably want it to be a single instance and have it running quickly as a Node.js instance, perhaps in here doing all that. There is a node for, I'm just trying to find it here, the Revolution Pi, this Rev Pi read node, and there's a write node which will allow you to put in a name, an offset, and a bit. So it'll only do bits, it won't do words or other things, and the writer is basically the same. All right, where you can have a value, the bit, the offset, and just give it a name. But these rely on having a Python code, which then talks to, which does the file read and everything else as well. And I haven't looked at how these have been implemented, but really, I don't think that they would be any quicker than what I'm doing here. You just have the benefit that by using these modules, and if you've got Python loaded as well as the code, you just have to put in the offset and the bit, and you're a little bit more removed from the hardware, or at least the kernel software. In my case, let me just get rid of these. I am just executing a C program, which does basically the same thing as the Python program is doing. It's just a little more obvious here. I could wrap this up and bury it, but I didn't want to because I wanted you to see how to do this very, very easily and fully understand what's going on. So I think that's the end-to-end of what we've got here. So we've got the first one that I showed you. Oh, I twiddled the just to show you, I went and did a twiddle on the encoder switch a few times, and you can see here I've changed the count up to 446. I've got a counter numeric here. The up and down here will adjust this, but the very next sample that comes in, it will actually put that back to where the counter is. It'll overwrite it. If I wanted to have that do something, I would have to have a flow going out from the counter display, this numeric. I'm within this numeric control, I'm changing its value. You can see it's currently 438. It comes in here from the read into this and sets its value. By pressing the up and down on the control, if I can do it quick enough, let's go up a whole bunch, make it 60 something, quickly go back. You can see it's saying 462, but that will very quickly go back down to the actual encoder value. Okay, I think I just found a little bit of a bug in this numeric display. It is updating when I hit that. This says 455, which I thought was the current value, which it says. But when I look on here, it's actually back to 446. So if I do that again, take it up to 450, let's take it up to a different value. Let's just say 470. See, it actually reset itself right there. Let's take it up to 480, 500 nod. Here it says 500 nod. If I actually trigger it, it'll stay at 500 nod, but here it's already back to 446. So it was working. It's just there's a little bug on the debug output of here that didn't actually show me the revised value again. I think that's pretty much everything I want to show you in this video. All of these flows, I will export them into a text file and attach it to the post on DesignSpark so that you guys can download it and install it into your own instance of Node-RED if you want to play with this and see what I've done. If you don't have a Kunbus and you're doing this on an actual Raspberry Pi using GPIOs or something else, then obviously these PyTest read is not going to work for you, and you would have to put something else in here to substitute for reading from the Kunbus IO modules. But the Modbus functionality, etc., will still work. So if you had two different Raspberry Pis and they were both running Node-RED, you can have a Modbus reader running on one of them, because right now I'm also using an external module on the other instance of the Kunbus with the Core 3. But this Modbus, it's for reading and writing, so you can actually be a master and a slave. So you can send across to it, but at the other end you can have a Modbus server that is receiving those messages, and then you could be reacting to them at the far end instead of having a hardware-based one. So it's not a limitation. I just decided that I would try and use the Ethernet IP module that was sitting there. And we did get that working, no problem at all. So I don't know if there's anything else you want to know on this specifically. I will be doing some more videos using these Kunbus devices, both for potentially upgrading it to use the new RevPi, new Raspberry Pi Core 3 compute module, which has got the enhanced memory and processor speeds, etc., that was recently released. I will also be doing a separate video specifically on the Ethernet IP module, going into a little bit more details of how that works, and should be putting together a video to explain 4-terminal resistance thermometers and basically Kelvin connections in general for precision resistors, shunts, etc. They're all basically the same principle, so I figured that it would be a good opportunity to do a separate video on just how that works. For this though, I think we've done enough on this. I haven't really gone into how Node-RED works, and that wasn't the point of this video. I think the last thing I do want to show you is, so we've covered this, covered this. Yeah, the MQTT is basically a messaging service that there are, you can install it on a local machine. It could be Windows, it could be Linux, it could be Ubuntu, it could be even on a Mac. It's available for a lot of different platforms. I'm running it on a Raspberry Pi. And what it does is take messages in and will send them out to subscribers. It runs with a publish subscribe paradigm where you can declare a topic for publication. So in my case, one of the topics that I've got is, let me just pull one up here. Tele, and the hash here means anything after that. So if a message comes in with the topic of tele, T-E-L-E, / and then anything after that, it will, this is actually a subscription node, and that message will be forwarded from the MQTT broker to this node. So when this fires up, it'll actually reach out to it and say, hey, I'm interested in anything that starts with tele / and then anything after it. On here, for the stat one, I've actually, this is subscribing to a slightly different message that begins with stat. And for, there's one other one here somewhere, oh here, and this one is looking for any messages that start with CMND. They all basically work the same way, and these are all subscribers. The publishers are actually some ESP8266 Sonoff modules that I've got temperature sensors onto. I've got quite a few of them around the house, as borne out by, let me just look at sensors. You can see here I've got a couple of these are turned off right this minute, but 1, 2, 3, 4, 5, 6 different sensors set up around the house and outside the house. One of them has also got a pressure sensor. They're all running on Tasmoda software, and they're all connected to my home network via Wi-Fi. The switches I've got everywhere. You saw some of them here. All of those relays actually do have switches on them as well. So every 5 to 10 minutes, one of the switches, each of the switches, will send out a status update that says, hey, here's my current status. It'll tell me what the Wi-Fi signal strength is. It'll tell me the condition of the switch, whether it's on or off. So that could be a light left on or whatever it might be. And it'll send that out. And this particular little panel here is just showing me the status of those when they come in. So there you have it. I will go into more about how these other things work in other videos, not specifically about Kunbus, because at this point it would be just generic Node-RED and home automation kind of topics. So I'm not going to go into any more detail than that right now. If you have any questions, feel free to email me, peter@thebreadboard.ca, or post questions into the forum itself or on YouTube. And I guess that's it, and I'll see you on the next video. Bye.